Hello everyone, welcome to the GATE lecture series of SA Engineering College. I am Dr.S.BHUVANESWARI, Associate Professor, Department of EEE. First, let us go on to the GATE syllabus of power system. So power system is one of the major contribution of the GATE syllabus, where the power system is going to include basic concepts of electrical power generation, AC, DC transmission concepts, models and performance of transmission lines and cables, which is where I am going to concentrate today. Normally, in a transmission system, we have two modes of transmitting the voltage. The one is overhead transmission line, the other one is underground cables. First, let us see what is the classifications of overhead transmission line. Basically, a transmission line can be classified as three: short transmission line and medium transmission line, and then long transmission line. Based on the distance and operating voltage, it is being divided. Short transmission line can be categorized as the distance which is less than 50 kilometers and the voltage which is operating less than 20 kV are called as a short transmission line. And medium transmission line is the line where the distance covers between 50 to 100 kilometers and the operating voltage in the range of 20 to 100 kV. And long transmission line, so it is a distance covering more than 150 kilometers and the operating voltage greater than 100 kV. Transmission line can be designed and performed based on four different parameters. These four different parameters are given over here: the resistance, inductance, capacitance and shunt conductance. Transmission line can be modeled with a distributed parameters. See, all the four parameters we have discussed in the previous slide is going to be the part of the transmission line model, where you have the L, C, R and G as the modeling parameters of this long transmission line. VS stands for the sending end voltage and VR stands for the receiving end voltage, and this is a complete transmission line model of a long transmission line. And here you can see series impedance. So the series impedance is going to be contributed by the resistance and reactance, especially the inductive reactance, and the shunt admittance is going to be decided by the conductance and the capacitive reactance. We will see one by one what are all the different four parameters. Resistance, we all know resistance is nothing but the opposition to the flow of current. See, this resistance is dependent on different parameters like the frequency of supply and the temperature and the conductor material, the length of the conductor and diameter of the conductor. We all know R is equal to rho L by A. So based on this factor, we have the three parameters: the resistivity and then the length and area. So these are the three main parameters which decides the resistance. Apart from that, the frequency of supply and the temperature also decides the resistance of any material. Coming to inductance. So in inductance, we need to know what is basically an inductor and what is an inductance, what is mutual inductance. After that, we will move on to what is actually it is going to give a part in the transmission line parameter. Inductor is nothing but a device that stores energy in the form of magnetic field. Inductance can be defined as the property of an electrical conductor or circuit that causes an electromotive force to be generated by a change in the current. And this causes an electromotive force is nothing but the voltage which is induced in the circuit can be given by E is equal to minus N d phi by dt. And here we can see N is nothing but the number of turns and d phi by dt is nothing but the rate of change of flux. Here I have omitted the negative part of this equation. Since we are going to concentrate only on the magnitude part, this negative part is removed in the next step. Here we can see this d phi by dt can be rewritten as d lambda by di into di by dt, where lambda is nothing but the flux linkages. Flux linkages is equal to the product of number of turns into the flux. and this d phi d lambda by di is nothing but the inductance. So the EMF induced or the voltage induced in a circuit or a coil is nothing but the product of the inductance into rate of change of current. So finally we can say that inductance is nothing but the flux ratio of flux linkages to the current. So we all studied what is inductor inductance, and here is the inductive reactance. So inductive reactance is the most important and dominating part in calculating the impedance of a line. Inductive reactance can be given by XL is equal to J omega L, and a steady state voltage drop due to the alternating flux which is flowing through the circuit can be given by V is equal to the reactance into the current. So reactance value is J omega L into the current. So that is going to give us the voltage, and here this lambda can be replaced in place of the product of L into I. So in the previous slide, here we have seen L is equal to d lambda divided by di. So in a steady state condition, L can be written as L by I. So in such case, our lambda is equal to L into I. So that's why this L into I can be replaced with lambda. Coming to mutual inductance. Mutual inductance is defined as the phenomenon of induced EMF in one coil due to the change in the current of another coil. So here we can give the mutual inductance of one coil. Say for example, I have given a notation M12, which is nothing but the mutual inductance in coil 1 due to the change in current in coil 2. So it can be given by the equation lambda 12 divided by I2. So here the whatever change happened, the flux linkages divided by the change in current in the second circuit is denoted by I2. So the unit of inductance is Henry. So M12 is equal to lambda 12 divided by I2, and the voltage drop in the circuit due to the current in circuit 2 can be given by V1 is equal to the reactance into the current. So again we have I2 into M12 is nothing but lambda 12. So in place of this M12 into I2, lambda 12 can be replaced, and the voltage drop can be obtained as J omega lambda 12. Coming to the flux linkages. Flux linkages are nothing but the product of number of turns into the flux. Okay, so here the flux linkage due to single current carrying conductor, which is what we are going to find. Why we are finding that? In order to calculate the inductance of a line, we must determine first the flux linkages. Without knowing the flux linkages, we are unable to find out what is inductance of a line. So we are going to assume a long single current carrying conductor with a radius r with uniform current distribution. So the current will set up a magnetic field. So due to that there will be a inductance all around the conductor. So here this inductance or the magnetic field is going to be divided into two based on the flux linkages, which is linking internal to the conductor and external to the conductor. So we can say like the total flux linkages of a single conductor comprises of flux linkages due to internal flux as well as the flux linkages due to external flux. First, let us see what is the flux linkages due to single current carrying conductor. For knowing that, we must know what is Ampere's law. Flux linkages can be found out from Ampere's law, from which the magnetic field intensity of a conductor can be calculated. So Ampere's law states that the line integral of a magnetic field intensity H around a closed path is equal to the current enclosed by the path. So here integral H dot dl is equal to I. So this is the Ampere's law, and this Ampere's law can be rewritten as, if there are n number of current carrying conductors, then it can be rewritten as H dot dl is equal to n into I. So this is the equation which is going to be the base for calculating the flux linkages of a single current carrying conductor, again which is the base for calculating the inductance of a conductor. first we'll see what is the flux linkages due to internal flux. Let us suppose that we are taking the conductor as conductor radius as r, and here from the center point the radius is r, and we are going to take up a path, say x radius and a thickness of dx for calculating a part of magnetic field intensity. So for that, let us take the enclosed path at a distance x can be calculated as dl is nothing but the perimeter. So dl is nothing but the perimeter. So what is the perimeter of the circle? It is 2 pi x. With a radius of x, we are taking, let us, this is the radius, right? So this is the radius x. So for this radius, this is a perimeter. So dl can be taken as 2 pi x. So the previous equation, h dot dl equal to ni, considering initially a single conductor or single turn conductor, n can be taken as 1, and h dot dl instead of h, at the point of x distance, the magnetic field intensity is going to be hx. So magnetic field intensity hx dot dl is equal to the current at point x at a distance of x. So here hx dot the dl value we can substitute from there. Hx dot 2 pi x is equal to ix. From there we are going to calculate the magnetic field intensity at a point x meter from the center can be given by hx is equal to ix divided by 2 pi x. Let us keep this equation as 1. And here we can see a graph. So in this graph we can see from the center the variation of h or the variation of magnetic field intensity due to the flow of current in the conductor with respect to the radius is given here. So whenever the radius is less than the complete radius capital R, here the intensity is getting increased. After the surface of the conductor, the intensity starts decreasing, and this is the characteristics of this internal flux linkage or the magnetic field intensity of an internal flux linkage. Flux linkages due to internal flux is continuing. Here the current density, as we discussed in the earlier slides, the current density is assumed to be constant. So with a uniform current distribution, so with a uniform current distribution we are starting off this equation here. So considering a uniform current distribution, we know current density J is equal to the current divided by area. So the current per unit area is nothing but the current density. So the current density at a distance of r meters can be given as current divided by area. It is the total current I divided by the total distance is r. So the area is pi r square, I by pi r square. Similarly, the current density at x meter, it is given by Ix divided by pi x square. And here, as we have assumed the current density to be uniform, we can equate these two equations. These two equations can be equated. So Ix divided by pi x square and I divided by pi r square. So from this we can able to come to a conclusion that the current at a distance of x is nothing but the total current into x square divided by r square. So let us keep this equation as 2. Now the flux linkages can be found out by first considering what is the magnetic field intensity. So magnetic field intensity at a distance of x can be given as Ix divided by 2 pi x. So this equation already we have derived. So Hx is nothing but Ix by 2 pi x. So from there we are just substituting the value of 2 in equation 1. So what happens? I into x square by r square into 1 by 2 pi x is given here. So x and x square are getting cancelled and we have only I x divided by 2 pi. Okay. So H is nothing but I into x divided by 2 pi r square with the unit of ampere turns per meter. So from the magnetic field intensity, what we are going to do is we are going to obtain the magnetic flux density. So we know the relationship between the magnetic flux density and magnetic field intensity. It is nothing but B is equal to mu into H. So this is the relation. So with that relation, we are going to find out what is the magnetic flux density at a distance of x meters. Here Hx into mu. Mu can be given as mu naught into mu r. So this is mu r. Mu naught into mu r. And again substitute whatever we got in the previous equation. Hx is equal to I into x divided by 2 pi r square. So that can be substituted here. So mu naught mu r into Ix divided by 2 pi r square. This is the equation for B. So that is what we have obtained, mu naught mu r Ix divided by 2 pi r square Weber per meter square. So the unit of magnetic flux density is Weber per meter square. So the flux d phi, again we know, after knowing the magnetic flux density, we must know what is the flux. Okay, so the flux d phi can be obtained for a cylindrical shell of radial thickness dx and axial length L can be given by d phi is equal to bx into A. This d phi is going to give us the total the flux in the radial thickness. So with the dx thickness we are going to obtain the flux, and once we get that we are going to obtain the flux linkages. After that, integrating the flux linkages, it is going to give us the total flux linkages which is there in the inside of the conductor. So here d phi is nothing but bx into A. So bx into area is nothing axial length into the radial thickness. So we have taken the axial length to be 1 meter. So 1 into dx is mu naught Ix divided by 2 pi r square into dx. So this mu naught I here, mu r is taken as 1. So for a non-magnetic material, here mu r is taken as 1, and now this is our d phi value, and from there we can find what is flux linkages d lambda. So d lambda per meter length can be given as the total number of turns which we obtained in the previous step, that is pi x square divided by pi r square into d phi. So here the pi getting cancelled, and what we get is mu naught I. So this is taken over here, mu naught I x, already one x is there, here x square is there, so it is mu naught I x cube divided by 2 pi, here square and here a square, it is going to be 2 pi r power 4 into dx. So this is the unit of flux linkages per meter length, it is Weber per turns. So then how to find out the total flux linkages? So the total internal flux linkages can be obtained by integrating the flux linkages what we obtained for that radial thickness dx. So the internal flux linkage, can be obtained by integration. So what expression we got? Mu naught I x cube by 2 pi r power 4. So that into dx will give us the internal flux linkages. Integration is mu naught I divided by 8 pi. So next step is to find out the flux linkages which is external to the conductor. Here flux linkages due to the external flux. So the external flux extends from the surface of the conductor to infinity. So we will consider the radius here from the center of the circle or the conductor, the radius is r. From there we are going to take up what is the flux linkages away from the surface of the conductor till infinity. Here the magnetic field intensity at x meters initially we will take, and for a radial thickness terms of dx, we are going to identify what is the magnetic flux intensity, and then we will extend it up to a distance of d or infinity. And here, as per the previous derivation, here we have the magnetic field intensity formula can be given as Hx is equal to I divided by 2 pi x ampere turns per meter. And as per the relation between the flux density and magnetic field intensity, Bx is nothing but mu h. So substituting the value of Hx here, mu naught mu r into Hx. So mu naught into I divided by 2 pi x. Here we can replace this mu r with 1. As I said, it is for a non-magnetic material, mu r value is 1. Now we are going to find out what is the flux d phi. D phi is nothing but B into A. So Bx into A. As usual, here the A can be given for a axial length of 1 meter for a thickness of dx. We have taken this, and Bx value from previous step, mu naught I divided by 2 pi x into 1 into dx. And here the d phi is finally obtained as mu naught I dx divided by 2 pi x. Here the flux linkages are equal to the flux, because the flux phi links with all the conductor away from the surface of the conductor only once. So n is 1 here in this case. So now integrating the obtained expression d lambda, we are going to obtain what is the flux linkages external to the conductor. So the flux linkages external to the conductor can be obtained by integrating the previous equation. So mu naught I dx divided by 2 pi x. Since we have taken the range of or the limits as r to infinity, we have applied here. It may be varied based on our need. Either it can be up to a particular distance d. Here these are the constant mu naught I 2 pi can be taken out, and x is the only parameter which is getting integrated, so that can be given as the total one can be given as lambda is equal to lambda internal plus lambda external. So lambda internal value is mu naught I divided by 8 pi plus mu naught I divided by 2 pi integration of r to infinity 1 by x dx. So here we can see this mu naught I divided by 2 pi is common in both the terms, so we can take it out, and 1 by 4 will be kept inside in the first term, and the second term integral r to infinity dx by x is the total flux linkages of the single current carrying conductor. So after we know the flux linkage, we could be able to calculate what is the inductance easily. So we know the relationship, right? Lambda divided by I is nothing but the inductance of a single current carrying conductor. So this expression divided by I is going to cancel out the value of current, and we are going to obtain the inductance. So inductance is equal to mu naught by 2 pi into 1 by 4 into this expression. So this is the inductance of a single current carrying conductor. Now further we can able to simplify that. How can we simplify? So we know the value for mu naught as 4 pi into 10 power minus 7. So L is equal to 4 pi into 10 power minus 7 divided by 2 pi will give you the simplification first step, and here after integration this is ln infinity by r. Here let us take the limits from r to a particular distance d. So within that distance I am going to find out what is the external flux linkage or external inductance. So the upper limit is turned to be d. So ln d by r. Now after cancelling out the terms, we are going to get 1 by 4. So, since we have a ln term in the second of this equation, here we have a constant. So I am going to change this constant with respect to the ln. So I can take 1 by 4 as ln e power minus 1 by 4, which is equivalent to the constant 1 by 4. And Then simplifying the ln terms, it can be taken together. This can be taken to the denominator, and ln d divided by r into e power minus e power 1 by 4. Here we can see after this simplification process, we can obtain the value of r dash. R dash can be given as 0.7788 times of r. So this is the finalized equation for a inductance, and inductance is equal to 2 into 10 power minus 7 ln d by r dash. So this r dash is nothing but a fictitious conductor radius. So the final inductance of a single current carrying conductor is 2 into 10 power minus 7 ln d by r dash. The unit for inductance is Henry. So this is all about the single current carrying conductor inductance. We'll see further topics in the next videos. Thank you all.